Do it again. Say hi to the internet. Hi to the internet. All right. Welcome all. We'll be starting in about 10 minutes.
Okay, I'm going to call the meeting to order. Good evening, everybody. Welcome. I'm seeing a lot of people who I have never seen before, which is really cool. And part of that's probably because
For the camera.
I have missed a couple of meetings, so it could just as easily be my fault. I'm glad to see everybody here on a lovely, warm, but pretty awful night, in all other respects. Although as somebody commented to me, at least we're not missing stargazing tonight. There's nothing to see up there unless this was the Delaware Valley Amateur Cloud Watch, which is just easy, which would be a lot cheaper, not needing as much equipment. So let's just go right to our reports, and we start with our membership report, and there is a lot to report. All right, isn't that?
Use your mic back here.
Use your mic.
We have 7 new members, Mark Stefan, Lydia Fan, Bill Montgomery, Erica Swinland, Paul Curtis, who was here tonight, and two members that joined tonight, Stephen and Sylvia Steinberg.
Welcome to all of you. A little bit of club business. We are having a business meeting, the 11th? I think I said the 11th. It's a Sunday. And we are a nonprofit corporation, a 501c3, and we have bylaws and procedures we have to follow. And that also means we have some deadlines for when I hate to talk elections now, but I have to, because the club has to elect new officers. Some of our offices, treasurer and president in particular, are term limited. So we don't end up being a right-wing fascist club. And both Lewis,
Just fact.
right, just fascist.
I don't know, the president for life.
Right. So I'm term limited and Lewis is term limited. So we, fortunately, Janet Rush has been really probably doing a better job at vice president than I have as president. So, and she will likely step up as president, which I'm delighted. We need a vice president. Our current vice president has to step aside due to health reasons. We need a treasurer. It's not that involved, and it gives you an opportunity to really contribute back. And one thing that has always amazed me in my 6 years of being an officer of this organization is it's really run by the members, the outreach, star parties, the programs at libraries, programs at schools. People show up, and I'm delighted to see that. I would love it if people would show up and somebody would volunteer to take the role of treasurer and think about being a vice president. I have been reaching out to people on the side, but not everybody has been interested or is intimidated or thinks it's extremely difficult. It's not.
It isn't.
It's not difficult. It's not a part-time job. I still practice law full-time and I can still do this. So it's doable. We would love your help. And I'll just say my email again. It's the best email. This is the one thing I'm gonna miss. It's president@dvaa.org. That is so easy. You don't even have to spell it.
Wow.
Email me if you have any interest. We'd love to have you involved. We really would.
Could we make an email Lane Duckett?
Sure, why not? Why not? So since you're talking, I think we go to the treasurer next. So Lewis, you're on.
Great. Hi, I'm Louis Berman, soon to be ex officio treasurer. Please replace me. I don't listen to whatever I say. That leads to comprehension. So it's that time of year. We're going to start bombarding you guys with emails. Please re-up. Your money helps us. It helps us pay, as I just paid a few minutes ago, a stipend for speakers and for other events. It helps us follow our mission of bringing astronomy out to people. And so super easy to get registered. It is, you go to the website, you'll see if you log in a $ next to your name. You'll also receive emails, which is a click through to do the thing, use a credit card online. Couldn't be simpler. And if for whatever reason you can't get it done, it turns out that we have real live tech support people. So on the top right of the website, it says support. It shows you a phone number, call them, they'll make sure you can log in if you have problems logging in, and then we really appreciate your money that helps us as I say do our mission. So thank you very much.
Thanks, Lou. We do not have an observing report, correct? Okay, I didn't think Janet sent us anything. That's partially or no small measure from nobody does any observing in November, December anyway, except on their own. So we're not doing any program. However, we do have a star party this Sunday at Valley Forge at 5 o'clock, starting at 5 o'clock.
I didn't realize that.
And we need telescopes there. We need people there bringing their scopes. I unfortunately will be out of the state. And I know Janet's away as well. A couple people on the IO groups page said they would be there, which is great. But if you have interest in coming, bring a scope. A lot of eyeballs, lot of people there love seeing what they can see. And at 5 o'clock start, that means that there'll be more kids. So it's a real kick. The first time a kid looks at Saturn, I guess Saturn's still up. Or particularly now Mars and sees it, and it flips them out. It's really exciting.
And Saturday looks to be.
Saturday is going to be a little windy. That's why I think we moved it to Sunday.
Oh, it's Sunday.
Yeah, we moved it to Sunday.
Okay, Sunday is looking
It's supposed to be
good,
very
partly
windy.
cloudy.
Yeah, very windy tomorrow.
Okay.
The final call will be made, pay attention, the final call will be made by 3 o'clock on Sunday. But if you can, please bring a scope out.
You have 5 exactly, or can you do that?
No, you don't have to be there exactly. Just come when you can.
And I'm gonna be there and I'll bring a scope.
Great, fabulous.
I didn't realize it was.
The address on the left?
Yeah,
Yes, it's at Valley Forge Model Airplane Field.
yes.
And we're not allowed on that field until darkness falls. And sometimes they're still on that field with their airplanes till right up to the very end. That said, that's a lot more comforting than when we're at French Creek, when they're on the firing range until very close to darkness and we have to wait. I much prefer Valley Forge. Pardon?
So move that way so someone can
Oh,
see.
I'm not as
Not in the camera.
intimidated by airplanes as I am by high-powered rifles.
Yeah.
All right, let me think. Louis, you had a report. Lou.
That's our new thing.
Hi, I'm Lou, Chair of the Astrophotography. If you guys don't know me, we have workshops once a month for anyone that's interested. Just look on the events calendar. There's a link with the credentials. You can show up. You don't need to register. But our next meeting happens to be December 7th, which is the exact day of Mars opposition. And we have a guest speaker coming to us live from the island of Cyprus via Zoom. He's an excellent planetary photographer. His name is Agapios Ilia. He's been with us before. And don't be afraid by his name. His English is very good. He's very, you can understand him. Probably much better than you can understand me. But at any rate, what we're going to try to do is, weather permitting, Agapios will have a live view of Mars as it traverses the sky, and we will have one of our telescopes, at least one here, and we're going to try to do a comparative view of the 2 or 3 different scopes from a vantage point of what I think Cyprus is like 6,000 miles away. So we'll see if we can measure the tempocentric parallax and maybe observe the differences in weather, atmospheric changes. So it'll be really, really cool. So you don't necessarily need to be interested in astrophotography. This is real astronomy. If you want to join in, all you have to do is click on the credentials. The meeting starts at 7:30. I assume something like this will last a few hours. So if you don't make it there at 7:30, just show up as early as you can. Anybody have any questions? If they're 1 plus UTC, so I think it'll be 12:30, when we start. It'll be 7:30 here, so, Mars will be already past the meridian in Cyprus. Anything else?
We were in the National Club.
At 10:30 that night, there's a Moon-Mars conjunction. So the timing is really good, although it should make the photography interesting because clearly you, both from here and from there, you'll be looking at Mars relatively close to the moon.
Yeah, Mars is bright enough, so that wouldn't.
Yeah, you'll be all right. Yeah, that business meeting is 2 o'clock, December 11th. Everybody is invited. It will be at my home in Ballackinny. My wife doesn't know that yet, but it will be at my home in Ballackinny. Okay, and with that, Jeremy.
First, we have a little something from Bill. By the way, I'm Bill McGeaney. I grew my hair out. Let me bring that up here. He couldn't be here tonight, so he left this recording for us.
We dim the lights? Yeah.
Yeah.
There we go.
Guinea here, just hoping to gauge some interest in partaking in some DVAA organized camping trips. This is something we've done in the past and we kind of got away from over the past number of years, but hopefully we can maybe make a good attempt at it in 2023. In the past, the DVA has done group trips to places like Cherry Springs State Park and Blue Mountain Vista Observation Field. I can speak from personal experience that there's really nothing like a DVAA camping trip. It's the stuff DVAA lore is made of. It's not odd to witness spontaneity of a random jam session before dusk. I know that one year up at Cherry Springs, we had Gary, Lou, and Nate all bust out their musical equipment and just start playing. You get to visit some interesting and local tourist traps in different areas. There's some hiking you could do during the daytime, fishing, you can do a whole bunch of different things. Most of all, you get to be on the same field as other DVAA members. And I can't underscore that. At night, it helped me out, especially when I was beginning as a member of DVAA, to go out to different observation nights with friends that I've met in the club. And this is a way for you to expand your friendships and also gain some really good knowledge about how to do certain things or where certain things are in the sky, expand some of the visuals you're trying to find, some of the objects you want to find that night. So I put together a survey to ascertain the accessibility needs of the club, determine locations we'd be willing to visit, and how far we'd be willing to go. This by no means is exclusive. I'm very interested in hearing any thoughts you have, and I encourage you to reach out to me with any ideas. At the end of the day, for as much as we're all introverts, there's something fun that happens when we're in the field together. Joe Lamb once said that astronomy is really a social experience, and nothing better exemplifies that than spending a weekend under the Milky Way with your fellow DVAA members. So take a look at the survey. I can't wait to see what we can put together in 2023. And reach out if you have any thoughts or ideas. We'll see how we can make it happen. Thank you, everyone.
So I don't know could you all hear that? All right, so I'm gonna repeat essentially what he said. Bill is taking over as camping czar. We have done a series of overnight or multiple night star parties, and we've done those at a variety of locations. We've done them at Blue Mountain Vista. We've done it at Cherry Springs, which is a dark sky heritage site in Potter County. How many of you have heard of Cherry Springs State Park? Okay, it's an amazing place to visit if you've never heard of it. Lou and I have talked about how the Milky Way is so bright, it's almost like a fluorescent tube overhead, like a work light. But we go up as a group and we meet up there and we have organized activities and there's other things to do. One year, George Caton arranged for us to do some digging into some of the rocks on the side and digging for fossils. There's a railroad museum up there. There's a cave in the ice mine. Yeah, there's the ice mine. Some of us have also gone to the Grand Canyon of Pennsylvania, which isn't too far away. Once you're 4.5, 5 hours plus from Philadelphia, another hour trip to the Grand Canyon is not that big a deal. But it's a lot of fun and it's a great opportunity to do stargazing with other people and you learn an awful lot. A lot of the stuff I've learned and I know next to nothing has been at these star parties. Like I think I can find Homer Simpson's underpants now, and stuff like that. So he's got a QR code. I'm going to try and get that. I'm going to suggest that's put in the newsletter so that people can scan it. And we'll put something out over DVAA's email. And think about it. No, we don't go in January or February. We go. At one point we were thinking about a March Messier tour, but that never happened. But we generally go in the summertime, June through August or September. Brian, did you want to say something? Oh, it's on the website too. Good. So I'll have them put it on the website. Yeah, that way y'all can watch it again. But think about it. It's a lot of fun. Okay.
Camping good, Bill making camping even better. It'll be great.
Yeah, and Bill will camp when it's 20 below zero. He's amazing.
Exactly.
So and I'll just tell you, I went up. One of the trips I went up, this was incredible. I went up. I had all my equipment, had my list, bought everything I needed. Went to set up my tent. I hadn't brought any tent poles. And Lou had an extra tent in the back of his car. Saved my rear end. I had a great time up there. It was really amazing. So yeah, it's a lot of fun.
By the way,
I don't tell people about the white knot.
They can learn about the late Nazi while they're out there.
yeah, I just took the survey. It took 3 minutes. It was very easy to do. And apparently Bill is asking if we can go further afield.
Yeah, we've
time.
explored that. We've explored West Virginia and stuff like that.
Yeah.
And, it's
Wouldn't mind doing
possible.
that. Yeah.
It's possible, as long as it's dark.
Mhm.
All right. Jeremy, back to you. Michael?
Yeah. All right, so I do have to take exception with one thing you said about nobody observing in the winter. I just got my email from Dave Creevy at Obsession last night. My 18 inches on the way.
Yes.
Should be arriving around Thanksgiving, so I'm expecting December to be out at least Green Lane. If anyone wants to join me. Brian's volunteering. All right. All right. Hopefully we'll get some people out there and we'll get first light for it. And actually on that topic, the December meeting, the topic will be winter observing. So we're going to have a couple of presentations about observing in the winter, what to wear, what to look for, how to prepare for observing in the cold and lasting those long nights. So that'll be our meeting on December 9th. But this month, we're very pleased to have a returning champion come back to us, and actually one of our members. Rick Schwartz is a DVAA member, and he's also been very actively involved in astronomy research. So Rick completed his PhD in biophysics and physiology from the Rensselaer Polytechnic Institute. And since then, he's spent about 40 years working in the biomedical field. He's been very instrumental in discovering and developing therapeutics for cardiovascular medicine. He worked in a number of different fields, most recently as the president and founder of CV Ventures. Now, in addition to that, he's been very active in what's called the TESS collaboration, and I forget what that acronym is, but I'm sure Rick will explain it. As part of that, he's conducted over 1,400 observations, which have contributed to over 50 publications regarding exoplanets. And actually, at last year's TESS Science conference, he was given an award for being the most prolific or productive amateur contributing to the, not the most obnoxious.
There's next year.
Yeah. Yeah, so Rick gave a presentation a couple of years ago about the work that he's been doing, so we're very pleased to have him back again. So please join me in welcoming Rick Schwartz.
Well, thank you very much, Jeremy, for that most gracious introduction. With the wireless walk-around microphone, it takes me back about 25 years when I was a guest MC on the Jerry Springer show. And I really wasn't, no, never. But I was going to say if I had been, I'd have a lot of chairs thrown at me, and hopefully that won't happen tonight. Yeah. Exoplanets, planets around other stars. The first exoplanet was discovered by DVAA and his mentor Michel Mayor of the University of Virginia in 1995. 50 light years away was 51 Pegasi b at half a Jupiter mass, and as we were all astonished at the time, a 4¼ day orbit. It was the prototypical hot Jupiter, 1200 degrees Kelvin. By way of reference, Jupiter in our solar system is 1000 degrees Kelvin cooler than that, and is on a 12-year orbit. So the very first thing to come out about exoplanets was it seems as though there's little resemblance to the planets in our solar system. For this seminal work, these two gentlemen were awarded the Nobel Prize in Physics in 2019. As of yesterday, November 10th, according to the NASA Exoplanet Archive, there are 5,197 confirmed exoplanets. On average, it's known from statistical work done by G. Mulders at the Lunar and Planetary Institute in Arizona, that each star in our galaxy has at least one planet, probably more than that. Work by Danley Zhu and Eric Ford at Penn State. A statistical analysis has shown that it's estimated that 1 in 4 stars like our sun has an Earth-sized planet in this size range, about 3/4. Keep hitting the wrong button here. About 3/4 to 1.5 RE Earth radii in an Earth-like orbit of 237 to 500 days. Sure.
That figure of 1 planet per star.
Yeah.
Does that include orbiting a binary?
Yes. Yeah. As a matter of fact, I'm going to show a couple of examples of the circumbinary planets that we've observed.
So it has 2 planets then?
No, I mean it's per star. If it's a circumbinary and it has, if it's a binary star and there's 1 planet circling one of the stars, that's figured into that. If there's 2 planets orbiting one of the stars, that's figured into that too.
It counts the binary.
Yeah. Yeah. And work by Eric Pettiguro when he was at Caltech, he's now at, when he was at Berkeley, he's now at Caltech, has shown that it's likely that there are 30 to 40 billion Earth-sized planets in the so-called habitable zone of their host star. The habitable zone being the distance from the host star where the temperature is conducive to liquid water on the surface and the possibility for life. The 16th century philosopher and scientist Giordano Bruno, in his treatise, The Infinite Universe and Worlds, said that there are therefore innumerable suns. There are infinite Earths that equally revolve around these suns in the same way that we see these 7 planets revolve around this sun that is close to us. Bruno didn't base this obviously on any hard scientific knowledge, but he was prescient, given that what we've learned in the last 27 years, but his beliefs and his professions were considered heretical by the Inquisition. He was imprisoned, he refused to recant, and tragically, he was executed in 1600. The 19th century poet laureate, Lord Tennyson, was eulogizing his good friend Arthur U. Hallam in 1883, and he spoke these words. Obviously, I don't think he was talking about exoplanets, but he might as well have been, because while we have discovered so many worlds so far, there's a real palpable sense of excitement in the field of what's going to come, and we really only scratched the surface, and there's a lot of excitement about what is to be. I have that excitement in me, and I hope I can share some of that with you tonight. I divide the science of exoplanet into 4 categories. People in this field that know a lot more about it than me might think a little differently, but I think for the most part, we would arrive at the same place. First, exoplanet demographics, which is very simply just that population study, their occurrence. I'm not very good with the clicker here. Occurrence rates and physical properties, their size, planet radius, mass, and their orbital architecture. Exoplanet characterization, where you get into what the planet composition is, its atmosphere, what gases, its surface, if you can get surface spectroscopy of the surface. What is the planet made of? How do you drill down and get more details about it? Exoplanet formation, how planetary systems come into being and how they evolve. And then finally, probably the least well-developed area, but the one that is the most exciting to a lot, is exoplanet habitability. What planets might have the right set of circumstances to have the potential to host life as we know it, or maybe even as we don't know it. When you get at these 4 questions, as far as I can see, you're asking 2 of the most fundamental philosophical and scientific questions that we humans have pondered since we've been around. Where do we come from? Are we alone? I'd like to cover 4 topics tonight: a brief overview of the test mission, the test follow-up observing program that I'm involved in, the ground-based follow-up program to look at the data and try to refine it that's observed on the test satellite. Observations that I've been intensively involved in. When Jeremy mentioned 1,400, it's now 1,500 observations that I've done and analyzed and reported using meter-sized telescopes at the LCOGT, Las Cumbres Observatory Global Telescope Network. I'll describe that network in some detail. And then most excitingly, some results that I've been directly involved in and their impact on exoplanet science. First, a brief overview of the test mission. The leadership is George Ricker at the Cobley Institute at MIT in Boston. He's the principal investigator. The science director is Dave Latham at the Harvard Center for Astrophysics, with which I'm affiliated. Dave and Karen Collins, who heads up the photometry subgroup, are effectively my bosses in the test organization, and I'm accountable to them. NASA Goddard Space Flight Center is the program office for the mission. The Ames Research Center in California processes a lot of the data in its pipeline. Northrop Grumman, the successor organization to ATK, by acquiring ATK, designed, built, and launched the satellite. And the Space Telescope Science Institute in Baltimore is the final repository for all the data we generate. The TESS satellite was launched 4.5 years ago in mid-April 2018 on a SpaceX Falcon 9 launch vehicle, as shown in this movie. It took 3 months following launch to establish the orbit that it's in, to commission it and perform calibrations. The primary mission began in mid-summer of 2018 and was a 2-year all-sky survey that ran until June of 2020. I'll talk about that sky survey soon. Following that, there was an additional, following that with NASA funding, there was a first extended mission that went from mid-2020 to September of this year. And an additional tranche of NASA funding was just provided. And we're now in the beginning of the second extended mission, 36 months long, that'll take us out September of 2025. This is the TESS satellite that is up there doing its work. There are the solar panels and the high gain antenna here. Most importantly for what we do, though, is the 4 cameras shown in the circle. Each of them are oriented to survey a separate 24-degree by 24-degree section of the sky. When you put 4 of those together, you have a combined field of view of 24 degrees times 96 degrees. Each camera forms the image on a 4 CCD mosaic shown here, and it works at an operational temperature on the satellite of -75 degrees centigrade and has very low dark current and read noise. Many people in this room are familiar with CCD camera specs, and these are impressive. These were custom designed cameras built at the MIT Lincoln Laboratory. How is this all-sky survey done? Well, as I said, each camera's field of view is 24 by 24 degrees. And when you put 4 of them together, you get a 24 by 96 degree field of view from the ecliptic to the ecliptic pole. And then in a what's called a stair and step protocol, it moves to the next observing sector approximately every 27 days. 13 sectors in the summer hemisphere were done in year 1. The spacecraft reoriented, and an additional 13 northern hemisphere sectors were done in year 2. And as I mentioned, this entire cycle was repeated between 2020 and the middle of this year, and we're now on the 3rd cycle of 2 all-sky surveys, northern and southern hemisphere. We use the transit method with tests, and by transit I mean when a planet is chance aligned so that it will go in front of its host star, it produces a dip in the light curve as shown here. Now, importantly, a larger planet as shown, or smaller planet as shown in this light curve, produces a shallower transit than the larger planet because less of the star's light is blocked out. So the depth of the transit light curve depends upon the size of the star relative to the planet relative to the host star. Also importantly, and this is a bit obscure, but the duration and the slope of the ingress and egress, the ingress being when the transit starts, the egress being when the transit completes, depends upon how close the transit is to the stellar equator. If you look at the smaller star, it produces less of a sharp slope and a shorter duration as compared to the larger star, which has a shorter slope of ingress and egress and a longer duration. So therefore, importantly, the transit light curve data convey important information about the planet-star system. This is really just scratching the surface. We collect a lot of parameters in the observations. There's a very complicated mathematical modeling computer program that we work on our desktops to analyze the data. It's iterative, it can be frustrating, it takes a lot of hammering out, but at the end, you can usually learn a lot about the exoplanet system. The test mission status as of yesterday, a total of 6,052 test planets and planet candidates have been identified. These are in addition to the approximate 5,000 confirmed planets that I mentioned previously. These are planet candidates. They don't yet have to have a measurement of their mass, most of them, so they're still called planet candidates. A recent analysis and projection by Michelle Kunamoto at MIT has said the test will likely discover at least 12 to 13,000 new exoplanets. I actually think that, my humble opinion, that's a conservative estimate. And Michelle presented some additional data a couple of weeks ago at the Test Science Conference in Boston that I attended. And it looks like this is holding up very well. And these projections are actually in very good agreement with projections that were made by Tom Barclay at the Goddard Space Flight Center in 2018, that he made some projections as to what the yield would be, and it's turned out that he was pretty much spot on. George Rickert, the PI, pointed out that during the ongoing second extended mission, we will probably observe an estimated 400 million stars for potential transits with brightness down to visual magnitude of 18. So it's going to be quite a comprehensive survey. Quickly, the test follow-up observing program that I'm involved in. There's actually 5 parts to it. I'm going to run through them quickly. The first one, the one that I'm involved in, highlighted here, is the Seeing Limited Photometry group That's the one where we take the observations from the scopes and the cameras and analyze intensely the transit data, looking for exoplanet signals and exoplanet modeling in the data. Other subgroups, I'll flick through these quickly in the interest of time, but reconnaissance spectroscopy to learn more about the physical characteristics of the host star. High resolution imaging to try to separate out nearby neighbors that could be contaminating the signal. Nearby stellar neighbors, I should say, nearby in the sky. Precise radial velocity work, radial velocity using the Doppler effect to try to find out the mass of the planet and the star. And finally, space-based photometry using other satellites like Spitzer before it was decommissioned, the Hubble Space Telescope, and now James Webb, in order to gather more data. I'm only going to show this once, but it's to make what I think is an important point. This is a publication that appeared last year in the Astronomical Journal on one of the primary systems that I was involved in, one that will likely be imaged by the James Webb Space Telescope. We have a proposal in to do that. And what's notable about it is there are 62 authors. This is becoming increasingly common in physical science, but you know, down here, affiliation number 17 of 38 is little old Rick, surrounded by a lot of awfully smart people. That's one of the real joys of being involved in this. The TESS Global Science team is hundreds of very smart scientists on every continent. Yes, there's a telescope in Antarctica that is making observations and producing data. And they have vast astronomy and astrophysics expertise across all of these disciplines, photometry, spectroscopy, way down including mathematical modeling, engineering, and data science and coding. And I have found, as have many of my colleagues, that they are collaborative, cooperative, supportive. They're very generous in sharing their knowledge and their results. And we have a good time. They're just plain fun to work with. And it takes a lot of expertise to pull this off. And in a turn on a well-worn phrase, it really takes a village to discover an exoplanet. I'd like to talk about the telescope network that I've been fortunate to work in. This work is funded by a grant, which we're now in the process of writing a renewal for from the National Optical and Infrared Laboratory of the National Science Foundation. The LCOGT network is a global array of meter-class telescopes, 8 sites, 30 telescopes, 0.4, 1.0, and 2 meter apertures. I work mostly, not exclusively, but mostly with the larger ones, the 1 and 2 meter aperture scopes. They have very exquisite capability in precision photometry, which is mostly what I do. Other members of the team specialize in reconnaissance spectroscopy of the host star. They're all fully robotic and auto-scheduled. When we want an observation, we put down the right ascension and declination, the sky coordinates of the star target we want, the filter, the duration, the brightness, a couple of other things. And the auto-scheduler picks out the ideal location of the 8 sites on the Earth to perform the observation, does it automatically, dome opens, camera runs, dome closes, data are available usually within 5 minutes of the observation being completed. The data files are big, they average 10 to 40 gigabytes of data per observation. I am sure glad that I have a high-speed internet connection. It's needed. These are the 8 sites. I'll run through them quickly. The Haleakala Observatory on the island of Maui in Hawaii has a 2 meter scope that I do specialized observations with. I become the 2 meter guy on the team by my boss's moniker. McDonald Observatory in Fort Davis, Texas has a nice array of scopes. These are the 3 Northern Hemisphere observatories I should point out. Tate Observatory, Tenerife, the Canary Islands in Spain, is the 3rd Northern Hemisphere observatory. Southern Hemisphere, Cerro Tololo Inter-American Observatory in Chile. South African Astronomical Observatory in Southern South Africa. and Siding Spring Observatory in New South Wales, Eastern Australia. These are the thick scopes that I work with all the time. There are two others. There's a WISE scope. It's called WISE Observatory in Israel, which is purely spectroscopy, so I don't do much with that. And there's a 2-meter telescope under construction in Tibet, which is going to be a very powerful instrument located at 5 kilometers altitude. The scopes in the 1-meter network, this is an example. It's the McDonald one in Fort Davis, Texas. They're all Ritchie-Cripian Cassegrain optical path, which the parabolic primary and secondary mirror, as many of you know, eliminates off-axis aberrations, specifically coma. You get beautiful, even if it's defocused, nice, bright, distorted images right out to the edge of the field. The mount is an equatorial C-ring. The Hextech borosilicate is the material the mirrors are comprised of. They're for reflectivity overcoated with aluminum and quartz. Field of view 26 by 26. The pixel scale is very impressive at about 4/10 of an arc second per pixel. And the custom imager at the Cassegrain focus here is called a Sinistro camera, has a special name. I could tell a story on that, but it would take too long. It is a 16.8 megapixel camera with a pixel size of 14 microns, operates at minus 100 degrees centigrade. And again, as you can see, that has very impressive specs for dark current noise and also read noise. The 2-meter telescope that is presently at Haleakala in Hawaii that I use a lot is on an altitude azimuth mount. It's too heavy for an equatorial C-ring. The same mirror material. Smaller field of view due to the longer focal length and the bigger aperture. Has a pixel scale of around 1/4 of an arc second per pixel. The most fascinating thing and useful thing about this setup is the imager is what's called a Muscat 3. That is, it's a custom designed imager, but it stands for Multicolor Simultaneous Camera for Studying Atmospheres of Transiting Exoplanets. And its feature is that it has 4 independent fiber optic fed optical paths in 4 different wavelengths, 4 different passbands. So you can do simultaneous photometry in 4 different filters or colors. The blue G filter, the R filter, which is more towards the middle of the visible spectrum. The I is red and the Z is even redder. And this makes for very powerful specialized photometry to answer certain questions that I'll talk about in a little bit. Again, very impressive specs for the CCD. These are the pass bands of the filters I mentioned. The blue G filter, the mid spectrum, visible spectrum R filter, the red I filter, and the very red Z filter. You get a nice broad wavelength range here that you can cover. Okay, now it's time for some results and their impact on exoplanet science. There's going to be a little bit of setup on some of this discussion, which I hope you don't mind. First of all, I'll be presenting and discussing only findings and results that have been published in peer-reviewed journals. Jeremy mentioned that there's 50 that have appeared in print. There's another 80 that have either been accepted for publication. I'm a co-author on these with a cast of thousands, accepted for publication, under review, or etc., or just submitted. So far, of all the ones that I've been involved in, we haven't had a paper bounce yet. They've all been accepted. And I'm only choosing those for which I feel, and the team feels, that I've made a substantial contribution to the test science, meaning that I did most, if not all, of the photometry that characterized the exoplanet system. As of yesterday, that's a total of 1,508 observations that I planned, conducted, analyzed, and reported to the test science team. The key finding, as I mentioned at the outset, the key thing that we're finding over and over again, and it's one of the most provocative things to come out of exoplanet science, is that many exoplanet systems, if not most, bear little resemblance to our own solar system. Our own solar system, we'll go through this quickly, but as you all know, is comprised of the 4 terrestrial rocky planets that are dense because they have a heavy metal core and a rocky mantle and a solid silver crust. The ice giants Jupiter and Saturn much less dense because it is believed, although Juno satellite is changing our thinking on this, an icy rocky core and a liquid metallic hydrogen mantle and an extended hydrogen helium atmosphere. And the ice giants, Uranus and Neptune, that are comprised of an icy rocky core and a icy layer and extended hydrogen helium and in many cases methane or pneumonia extended atmosphere. However, when you look at a frequency histogram, which this is the number of planets per star on the y-axis, and this is their radius, the size of the planet, our symbol for Earth, it would be the ratio of the size of the planet to the size of Earth. So Earth is right here at 1. A couple of things jump out. Out here in this red box, where the ice giants and the gas giants are in our solar system, really very few exoplanets outside of our solar system have been discovered of that nature. Most of them are in this regime, planets that are larger than Earth, but smaller than the ice giants in the range of 1 to approximately 4 Earth radii. Super Earths comprise the smaller ones, 1 to 1.5 Earth radii, and so-called sub-Neptunes, smaller than Neptune, bigger than Earth, 2 to 4 Earth radii. And of course, there's a gap in here, the so-called radius valley that we'll mention in a little bit. This is a schematic of what I just said. Super Earth, 1 to 1.5 Earth radii, bigger than Earth, with probably a rocky core and a thin atmosphere. Sub-Neptunes, 2 to 4 Earth radii, comprised of a rocky core or a water ice mantle. The exact ratio is subject to dispute. There's probably a wide range, and extended hydrogen helium atmospheres. These two planet types comprise 50% of all known exoplanets, and they don't exist in our solar system at all. Now, some test data and results. This schematic is from a publication that I showed previously on one of the first systems that I was involved in, the TOI 1233 system. It's referred to as a compact 4 exoplanet system for an obvious reason. When you look at this schematic, all 4 of the planets that comprise the system are well within what would be the orbit of Mercury in our solar system. They only go out to about 0.15 astronomical units, an astronomical unit being the distance from the sun to the Earth. So they're super Earth and sub-Neptunes crammed in pretty tightly. The host star in this system, TOI 1233, is basically, I won't go through all the specs here, but it's basically a solar analog. It's about the same size, mass, and temperature and spectral type as our sun. So we're looking at a sun analog here. The planets themselves, the innermost planet, highlighted here, is a 1.5 Earth radii super Earth, and the outer 3 planets, 2.1, 2.7, and 3.1, are sub-Neptunes. These are the data, the transit light curves that were obtained from the test satellite. Real briefly, one of the reasons we need to do so many ground-based observations is because the test satellite, while very powerful as a wide field survey, has a pixel scale of 21 arc seconds per pixel. Very wide field, very short focal length, very big pixel scale. As a result, it's hard to pin down the exact spatial location within the star field that the event is actually occurring. It could be occurring on 1 or more stars. So we need ground-based observations to tease this out. But these are the light curves that were shown detected on the satellite for the smallest super Earth, and then going up in size, sub-Neptune. You can see the bigger the planet in terms of Earth radii, the deeper the curve. 1 super Earth, 3 sub-Neptunes. Just something of note, this planetary system, the stellar system, is actually the brightest sun-like star to host 4 exoplanets at VMAG 9.25. But just by way of reference, well, we say it's one of the brightest stars that we've discovered planets around. If you were to go out into one of these very dark areas that we just talked about a few minutes ago, you know, no ambient light, beautiful, dark sky, pristine observing conditions, and take your 2020 or 2010 vision and search for the dimmest star you can possibly see in the sky. This star would be about 1/200th the brightness of that dimmest star. And yet it's one of the brightest stars we're looking at. And most importantly, we're able to detect drops in brightness of 1 part in 1,000th against that star. So we're doing even dimmer stars than that. I'm going to focus in on this guy up here in the top right-hand corner, 123302, to make an important point. I did 26 photometric observations of this, and there's a reason for that. This light curve has 3 parts. The top blue dots, this is a plot of light intensity versus time. So during the transit, which starts right about here, the light drops, stays low, goes back up after the transit is over. This is the normalized raw light curve. This detrended light curve is a light curve that has been modeled and adjusted for certain noise factors, atmospheric systematics, systematic distortions in the optical path, tracking errors, et cetera, And the lower curve, the green light curve, is the detrended and fitted light curve. It's fitted using a complex, valid algorithm that is used for fitting curves to recurring data like this. And the results validated that the detections were exoplanets and not false positives. And I talked about this before, 1.1 part per thousand drop in brightness. But on the next slide, what we're going to do is focus in on this bottom curve and graphically blow it up a little bit. There's the bottom curve, the detrended and fitted light curve. And what I've done here is taken this portion, the ingress, blown it up. The red line is where the ingress was projected to start. The gray line is where the ingress actually started per our model. The red line for the egress projection, the gray line for where the egress actually started or completed. Compared to the prediction, the ingress and egress were 7 minutes late. Now, these are small changes for an exoplanet on a 6.2-day orbit, but they're important changes because repeated observation and modeling of these so-called transit timing variations were very useful to us to constrain the orbits and planet masses in this compact multi-planet system. So what are transit timing variations? Real briefly, if you have a host star and a single planet going around it, the orbital period can be expected, at least to a first approximation, to be quite constant. And if you measure it repeatedly, as the schematic clocks indicate here, with each orbit, it is going to show the exact same orbital period, the exact same time that it takes the planet to go around the star once. That's for a single planet system. You can expect the orbit to be quite reproducible. When you go to a multi-planet system, in this case, what has been added in is a larger outer planet, and you do the same timing mechanism. Again, this is just schematic. This is not exact. What one is going to find is that the gravitational tugging and pulling of the larger planet on the smaller planet is going to cause variations in the orbital period. It's not going to be the same repetitively. It's going to vary. And that variation can be used in a very complicated model as a way of determining the actual finer orbital characteristics of the system and whether there are additional planets in the system. Transit timing variations can be used to figure out the masses of the existing planets and maybe if there are more ones. By way of historical reference, if you know your history of astronomy, the planet Neptune was discovered when Adams and Leverrier made predictions about the orbit of Uranus and how its orbital timing was off because it was being tugged by an outer planet, which turned out to be Neptune. And when we found these transit timing variations, we, at the time, were starting a collaboration with a recently launched satellite by the European Space Agency called Cheops, was launched about a year and a half after TESS. And its task is to measure precise radii for planets that have known mass measurements. So it's to try to get a much tighter assessment of the mass and the size of existing known transiting exoplanets. And they imaged the TOI 1233 system. We have a collaboration with them, which is unimaginatively called CHESS, the Chaos TESS collaboration. And the Cheops observations improved the precision of the TESS observations, and also with the transit timing variations, actually, we discovered a fifth planet, a 2.0 Earth radii sub-Neptune on a 30-day orbit. So this compact 4 exoplanet system in one quick jump went to being a 5 planet compact planet exoplanet system. Turning attention to another one of the premier multi-planet systems containing super Earths and sub-Neptunes that TESS has discovered on its first several years of existence is the TOI 270 system. And I'm just going to cover this briefly to make the point that there's a lot of these critters. I should mention the spectral type of the star and its magnitude, a little dimmer, a little smaller, not as big, not as hot as the star I showed previously, the TOI 1233. But in this system, it was also a compact exoplanet system comprised of one super Earth, 1.3 Earth radii, and 2 sub-Neptunes of 2.3 and 2.1 Earth radii. And there are lots of these. I'll show a listing of them later. Okay, super Earths and sub-Neptunes. They're the most common type of exoplanet that's been discovered to date, but they're not present in our solar system. Does this tell us anything? Can the fact that this is true, can their existence and their characteristics provide insights into processes of planet formation and evolution? The answer is yes, but first let's just take a real brief tour of an overview of star and planet formation. Stars and planets form when a giant molecular cloud of gas and dust gets perturbed and collapses under self-gravitation. And as it collapses gravitationally, it forms a flattened rotating disk. Think of spinning pizza and how it flattens out as you spin it due to conservation of angular momentum. A protostar, a newly forming star, heats and depletes the existing gas in the dust through a process called photoevaporation. Dust condenses into large solid grains, which condense into planetesimals. And planetesimals move through the residual cloud of gas and dust and sweep up more gas and dust, accrete it to form fully formed planets, as you can see them doing so in these concentric rings. A planetary system is being formed. These giant molecular clouds that collapse to form stars are not figments of our imagination. They're not imaginary. They're not theoretical. Here is one of the most iconic ones, the Eagle Nebula, the Pillars of Creation, imaged by the Hubble Space Telescope in 1995. The Hubble Space Telescope, as wonderful as it was, is now being, parts of it anyway, are being replaced by the James Webb Space Telescope, which has 3 near-infrared cameras and spectrographs as shown here, and 1 mid-infrared camera, the MIRI camera shown here. And this has been imaging a lot of giant molecular clouds, galaxies, protoplanetary disks, exoplanets. And they went back and re-imaged this image of the Eagle Nebula, the Pillars of Creation from Hubble. And when it was done in the NIRCam camera, you got this. These images were just released a couple of weeks ago. There's the Hubble one. There's the James Webb. Much better resolution, much better ability to penetrate the gas and dust, uh, much better ability to image newly formed stars. When I say these are giant molecular clouds, we're not kidding. This distance is 4 light years. You could fit 8,000 of our solar system in this distance, 8,000 of the distance from the sun to Neptune, the last planet in our solar system could fit into that space. Quickly, we're going to zoom in on this area of the Eagle Nebula as imaged by the JWST NIRCam. And as you can see, I'm going to highlight these areas here. These red areas are hot protostars, hot, newly forming stars that are actually pushing the extant gas and dust through the giant molecular cloud. They're forcing it out with their radiation pressure and photoevaporation. And these areas that I've highlighted in the smaller boxes, you can see that they have a 6-armed diffraction type, are actually newly formed protostars a little bit farther along than the red areas that I just pointed out. Overall, these stars that you're looking at here, these protostars, I should say, are only 100,000 to 400,000 years old, which is neonatal in terms of star formation. Our solar system is 4.5 billion years old. These are a few 100,000 years old. We're literally witnessing the birthing of stellar and planetary systems. These pillars were also imaged in the mid-infrared instrument, as shown here, and those longer wavelengths are better at discerning gas and dust in the system. And the darker regions that you see, particularly here and down here, are denser areas of gas and dust. And these orbs, these protuberances, if you will, here are areas where the protostars are pushing but have not yet pushed off the dusty cloaks of gas and dust surrounding them. And here's, real quickly, another JWST image of the Orion Nebula, a portion of the Orion Nebula, showing protostars forming in it also. Okay, so giant molecular clouds really exist. So do protoplanetary disks. How do we know that? Many of them have been imaged by the Atacama Large Millimeter and Submillimeter Array in Chile. It's an array of 66 radio telescopes, 12-meter aperture each, and they cover a wavelength range that is about 1,000 times longer in wavelength than the visible light range in the regime of 0.3 to about 3.6 millimeters. And they've been successful in finding protoplanetary disks. One of the first, H.L. Tari, back in 2014. When I first saw this in the journal, I said, boy, that's a really good artist rendition of what that disk should look like. And then I realized I was looking at the image that they actually recorded. You can see the concentric rings where planets are sweeping up gas and dust and carving out planets. Another example that was imaged is the TW Hydri system, 8 million years young. And there is evidence from, oops, if you blow up this inset area here, it is believed, there's some speculation involved in this, that this is an Earth-sized planet forming at 1 astronomical unit, the same distance as the Earth is from the sun. And other ones, the PDS-70C, which it is believed to have a Jupiter-sized, blow this area up out here, a Jupiter-sized planet forming at 30 astronomical units. Okay, back to super-Earths and sub-Neptunes. Now that we know the general scheme of star and planet formation, what else have we learned about them that is hopefully long-term, not today, not tomorrow, maybe a few years from now, going to inform our theories of star and planet formation? Going back to the histogram of the number of stars per planet versus planet size, with Earth at 1 Earth radii being right here. Again, it's a 2-peak distribution. You can see the 2 peaks right here, one at around 1.4, 1.5 Earth radii, one around 2.5 Earth radii. And the super-Earths are in this band here of 1 to 1.5. The sub-Neptunes in here, 2 to 4.5. But what's this area in the middle? where it seems as though there's fewer exoplanets. The so-called radius valley between 1.5 and 2.0 Earth radii, where there's a paucity of planets. It's believed to be, in general terms, a transition region where possibly super Earths are accreting extended hydrogen and helium atmospheres and becoming sub-Neptunes, or alternatively, sub-Neptunes are having their hydrogen helium atmosphere stripped away by the intense radiation of the host star. And it's going to take a lot of work to sort this out, but it's believed that this is an observational consequence, this radius valley, of different processes of planet formation and evolution. So the questions are being asked now in repeated observations that are being performed with large ground-based telescopes and the James Webb Space Telescope and other space telescopes. How do exoplanet systems form both super-Earths and sub-Neptunes, since they start with the same building blocks in the protoplanetary disk? If the protoplanetary disk has concrete and stucco and wood, how do you get an exclusively built brick-built house built in the same neighborhood if those are your only starting materials? Something else must be going on that we have to tease out. Is the radius valley a transition region in which, as I said before, super-Earth rocky cores gradually accrete hydrogen helium atmospheres and become sub-Neptunes? Or do the sub-Neptunes lose their hydrogen helium atmospheres and become super-Earths due to photoevaporation, the intense radiation of the host star stripping off the atmosphere, or other thermal processes which we won't go into at this time? The super-Earths simply lack this extended hydrogen helium atmosphere because they form in a gas-poor region of the disk. Maybe they form in an area where there isn't much hydrogen and helium gas, and therefore they can't develop an extended hydrogen helium atmosphere. Or, as I said, do they form close in, only to have their atmosphere stripped away by thermal photoevaporation? Or one other possibility, since I won't get into it, but since the whole concept of planet migration is important in the whole discussion of planet formation, do sub-Neptunes accumulate these extended hydrogen helium atmospheres farther out from the host star where it's colder, only to migrate inward where they end up in their final place? How are we going to get at this? Well, if you take this, I'm going to list some exoplanets that I have been involved in observing and characterizing, and there are others, of course. There are many others, but I'm going to talk about these just to make an important point. If you look at the range of super-Earths, 1.0 to 1.5 Earth radii, and those sub-Neptunes, as shown over here, 2 to 4 Earth radii, here's a listing of them. There's also a bunch of planets that are actually in this radius valley. They're located between 1.5 and 2 Earth radii, right in between where the primary regimes are. This is so-called the keystone planets. They're planets, they're believed to be keystone planets, not because they come from Pennsylvania, but because they are a bridge, if you will, in the formation of either super-Earths and sub-Neptunes. But importantly, I'm going to highlight this here. The 270 system and the 1233 system and others are multi-planet systems that straddle the radius valley. For example, the 270 system that I spoke of before, there's one super-Earth and 2 sub-Neptunes, same planetary system, but a set of planets that straddle the radius valley. The 1233 system, 1 super-Earth and 4 sub-Neptunes that again straddle the radius valley. What additional observations and data will provide insights into super-Earth and sub-Neptune formation and evolution? And this is what is going on right now. Spectroscopy. If you break up the light of a host star by a spectrometer, in this case, a prism, you get a spectrum of wavelength. If you have the star going through the planet's atmosphere, you get the spectrum of the planet plus the star. You take the spectrum of the planet and the star, you subtract the spectrum of the star only, and you end up getting the light from the planet only. And then one can analyze, this is schematically shown, can analyze for various constituents like water, methane, etc. Many more than that. This has been proven to be feasible, and a lot's going to happen with this in the JWST, James Webb Space Telescope Early Reading Science Program, imaged a couple of large Jupiter-sized planets that were already well known and characterized. WASP 96D, which is half the mass of Jupiter, but 1.2 times Jupiter radii, so therefore is less dense than Jupiter, and referred to colloquially as puppy Jupiter. And exquisitely clear detection of water in an exoplanet atmosphere, as you can see from these four bands here, these four peaks. Water was detected in this puppy Jupiter, 1,150 light years away. Another well-known exoplanet, WASP 39b, 0.3 Jupiter mass, 1.9 radius of Jupiter, even less dense Jupiter, referred to as a super puff. I personally, the first time I heard that, I don't like the phrase super puff. It sounds like a breakfast cereal that kids should avoid. But, this resulted in the first detection of carbon dioxide in an exoplanet atmosphere. I was on a Zoom call when these JWST data were presented for the first time to a fairly broad audience, including a lot of test collaborators. And it's not corny to say that people were absolutely gushing when they saw this. They could not believe how powerful JWST is for spectroscopy and discovering the constituents of planets, exoplanets in their atmosphere. So this is going forward. JWST will provide important information on the composition of the atmospheres and surfaces of super-Earth and sub-Neptunes. There's been some work done on this over the past half dozen to 10 years already, but it's no disrespect to it. It's primitive compared to what's being done now. Along with other information about the star and planetary system, such as the mass and temperature and composition of the host star and its spectra, the architectural and orbital characteristics of the exoplanet system. Putting this all together in models of planet formation is going to inform and constrain those models further. And it's important that this isn't all going to come from space telescopes. Important data will also come from other large ground-based telescopes like the Keck and Subaru telescopes on Mauna Kea in Hawaii, the telescope in the Canary Islands, the very large telescope in the Atacama Desert in Chile. Okay, that's super-Earth and sub-Neptunes. In a last few remaining minutes, if I have a few more minutes, Jeremy, I want to talk about four more fascinating exoplanet systems outside of this whole topic that I've been covering. First, an ultra-hot Jupiter, TOI 2109b, one of my favorite exoplanets. A planet that is forming in a protoplanetary disk, actually in the process of forming, called the AU-NIC system. And then two gentlemen asked about multi-star systems, two multi-star systems containing exoplanets, TOI 455 and TIC 1729. And I bring these forward because they truly exemplify the diverse and exciting exoplanet systems and science that TESS is discovering. This is TOI 2109, the ultra-hot Jupiter. And it is ultra-hot because it is on, get ready now, a 16-hour orbit around its host star. Wow. This schematic is actual size of the star and the planet and their separation. That's how close it is. Can't imagine what it must be like other than that you get immediately fried to be on that planet orbiting that star. It is the shortest period gas giant yet discovered, and it's second highest planetary temperature recorded to over 3,600 degrees Kelvin. So hot, in fact, that one of the things we had to deal with is that it might not have actually been a planet. It could be a substellar object, the so-called brown dwarfs, spectral type LP and Y. And we had to find a way to disprove that and prove that it was a planet. So we needed additional evidence. What additional evidence do you go for? Well, What evidence is needed? It would take another 10 minutes to explain, and it's not worth it, but it is well known in transiting exoplanet science that if the transit depth is the same at all filter wavelengths that you look at, that is, there's no difference in the transit depth by color of the filter used, it's an achromatic transit, and therefore you can be sure it's a planet. However, if the transit depth differs at different wavelengths, that is, it has chromaticity, it's chromatic transit, it's likely to be a substellar companion or part of a binary star system. In this case, we knew the companion just from the transit data was too small to be a full-blown star, but it could be a substellar companion. So what do? We went back to the telescope I described previously, the 2-meter scope in Haleakala with 4 wavelength bands for simultaneous photometry. And we observed this in those 4 bands of, by the end of the presentation, I'll learn how to use my clicker. In the G band, the blue band, the mid-spectrum R band, and then the red and even redder I and Z bands. And here's what we found. On these light curves, first of all, in the G band, there was a transit depth of 6.5 parts per thousand in the blue end of the spectrum. In the R band, mid visible spectrum, transit depth was really not different at all, 6.3 parts per thousand. In the I band, 6.6 parts per thousand. And in the Z band, 6.4 parts per thousand. I'm going to click through these 4 again, just to make the point. If you just look at any one of these, but focus on the model fit lower green curve, the detrended fit light curve. Transit depths differ by less than 5%. That's within the error of measurement. So we were able to conclude an achromatic transit, and 2109 is definitely a planet, an ultra-hot Jupiter. And it really is an ultra-hot Jupiter. The orbital period, based on just the 3 years of observations we've been doing, we know that it's decaying, slowing by 100 to 750 milliseconds per year. This is going to be followed for quite some time to constrain the models of what's going to happen to it. We already know what's going to happen to it. We just know when. We just know it's going to be a long time in the future. But its ultimate outcome is eventual tidal fragmentation and stellar infall, which is a fancy way of saying that it's going to move too close to the host star, gravitational forces will bust it up, and the pieces will fall into the star and get burned up. I don't want to be around when that happens. AU microscopii system, it's a planet-forming debris disk. A debris disk is a protoplanetary disk that is just more advanced in its formation. So there's literally, most of the debris has gas and dust that's been swept up by the forming planets, but there's still some in the disk that has not yet been accreted. That's why it's called a debris disk. This was imaged not just by TESS, but the disk was also imaged by the Spitzer Space Telescope before it was decommissioned a couple of years ago. The AU microscopii system is a late-stage protoplanetary disk. Fortuitously, the disk is visible edge-on rather than face-on like the ones I showed previously. So we can actually have the happenstance of being able to detect a transit. And the first planet we detected in this system, AU MIC-B, is the same size of Neptune in terms of its diameter or its radius, but 3.4 times the mass, so it's more dense. And of course, it was detected by the transit method. Very notably, the Spitzer Space Telescope helps sort out the properties of the protoplanetary disk. There's dozens of papers being written to model this now. Because the star is young and hot and producing intense white light stellar flares, as shown here. You see these flashes of light and recorded here. It's young, it's energetic, rapidly rotating magnetic lines are being formed and broken. The first debris disk planet found by TESS. Transit timing variations produced the second planet, AU MIC-C, that I was the first to find based on those transit timing variations. And This is AUMC 4.2 Earth radii Neptune-sized planet. AUMC, a sub-Neptune planet. It is also possibly a third non-transiting planet, AUMC. How did we find this? Well, this is the light curve of AUMC with, as you can see here, transit timing variations. We made about 18, 20 serial measurements and model fits, and we were able to predict the time we thought for when we'd be able to catch AUMC. We missed it a little bit. We didn't catch the whole transit. We caught the egress, as you can see here, not the ingress, but we later caught the egress, the whole transit. Interestingly, though, unlike this time period when we were imaging the AUMC planet, where the light curve dropped, went back up and smoothed out, in AUMC, after the transit was over, the light curve kept going up. We believe, with good evidence from many other observations, that this is evidence of a stellar flare actually occurring as we're watching. So, because of its fascinating properties as listed here, it makes it an exciting target for in-depth study with space telescopes and other large ground-based telescopes. And it's going to inform and constrain models of late-stage star formation, disk and debris disk evolution, and sub-Neptune and super-Earth formation and evolution. I want to close by talking about, this will only take a couple of minutes, I want to talk about two multi-star systems containing exoplanets. This is kind of fun. As many of you know, 50% of the sun-like stars are in binary two-star systems or multiple systems, more than two stars. The stars orbit a gravitational center of mass. They orbit around each other. 200 multi-star systems have known exoplanets at this point, and there are two general types. S-type, in which an exoplanet orbits one of the stars in the multi-star system, and P-type, or circumbinary, where the exoplanet orbits the center of mass of the binary system. So you have the binary stars orbiting each other, and the exoplanet orbiting the center of the mass of that binary star system. The first type, TOI 455, multi-star system. This is an image that we got from the Hubble Space Telescope, and it turns out that it is a trio of three M dwarf stars. Stars B and C down here are known to orbit each other every 36 years. And star A and the BC pair orbit each other, the common center of mass, every 250 years. These are the light curves obtained from the test satellite. We did a lot of ground-based observations to sort this out. It was tedious, but one of the most important things we had to do is this looks like it's very well separated with the Hubble Space Telescope. With a lot of the ground-based observations, there was a lot of blending of these stars, and we needed to do very precision photometry to sort out that both of the exoplanet transits were occurring on star A. But when all that was said and done, we did come to that conclusion. And then when the paper was published, it contained the very provocative and evocative title of Three Red Suns in the Sky. And this artist's conception is what is believed. If you could stand on the surface of one of these two planets, you would see the bright A star up here and the two dimmer B and C stars down here, and you would be orbiting this system. It's just kind of fascinating to think of a place in the universe with three red stars in the sky. One last planet, TIC 1729. This is the circumbinary planet, where you have, in this artist's conception, a Jupiter mass planet orbiting around the common center of mass of a binary system. It was known from modeling the data that we obtained from transit data that the eclipsing binary system has an orbital period of 19.7 days. We also found out that the primary star and the secondary star were approximately equivalent in mass and about the same temperature as our sun. And it was a Jupiter-sized planet on a several hundred-day orbit. I'm gonna, in the interest of time, skip over the rest of this. But this is a model of what a binary star system would look like with a primary and secondary eclipse. The primary eclipse, the deeper one, when the larger star goes in front of the smaller star. The secondary eclipse, the smaller one, the shallower transit when it goes in front of there. As you can see, you could spend more time in that, but. And fortunately, in this artist impression, we were able to catch the planet initially transiting the primary larger star. And then 5 days later, we caught it transiting the secondary smaller star and putting all the data together in a very, very complicated paper that was led by Vesel and Kostov at the Goddard Space Flight Institute. We found out these characteristics of the host star and the host stars and the circumbinary planet. Gonna go over this. It's just multi-star systems with planets around them are a staple of science fiction. We're all familiar with the mythical fictional planet Tatooine of George Lucas' Star Wars saga. The home of Anakin and Luke Skywalker. You know, it's fun, it's fiction, but you know, truth can be stranger than fiction. And having shown you just those two examples of a binary star system, I think reality wins in this case. Truth is stranger than fiction. So, sorry, Tatooine. Test some closing thoughts, if I may, real quickly. 27 years ago in 1995, no one could have imagined that there would be ultra-hot Jupiters, super-Earths, and sub-Neptunes, and so much more. We all started thinking that other exoplanet systems, if they existed, had to bear at least some resemblance to our solar system. That may still be true that there will be some, but certainly it hasn't been borne out in the data thus far. It just goes to show you that the reality of exoplanets and the universe in general is often stranger than our wildest imagination. In the words of the well-known astrophysicist and science communicator Neil deGrasse Tyson, the universe is under no obligation to make sense to you. Not to you, not to me, not to any of us. When I look at all this, it fills me with a sense of awe and humility. We may be the most successful species on our planet, but our planet is just a small planet, one of 8 among the smaller, in around an ordinary star, one of several 100 billion stars in our galaxy, containing more than that, likely, in terms of other planets. In an observable universe of anywhere from several 100 billion to 1 trillion galaxies, likely with exoplanets in them. You know, we're small, we're humans, and our planet are small. In a cosmic sense, we're inconsequential and insignificant. But while I feel that humility, I feel a sense of inspiration and optimism because we're curious. We want to study, we want to learn, we want to know. We want to build elaborate space telescopes and satellites and put them out in space where we can't be, at least not at this development of technology. We want to take our brain and put it in a box and ship it out into Earth orbit or the L2 Lagrange point and get more data. And then follow it up with exquisite ground-based observations where we painstakingly piece this all together. And we want to know the answers ultimately to the questions, where do we come from and are we alone? And in the process of doing that, we discover so many worlds. And so as we began this presentation by quoting the 19th century poet laureate Tennyson, I'm going to close it with one last slide. A quotation from another British man of letters, the 16th century playwright, William Shakespeare. A dialogue from his play Hamlet, Hamlet to Horatio. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Thank you all for your kind attention.
Yeah, go for it.
Yeah, I'll come around with the mic.
there a model or something that determines the thickness or the ratio of the debris disk around the star, or whatever central forming star that, is it a certain range that you find these in? And what, have we figured out what offsets, like, our, for example, our solar system, not exactly, we're on an angle a little bit, to each other. So it's not exactly organized perfectly.
Yeah.
So what tilt, what factors play?
Well, first, there isn't, at this stage of science, there isn't one model, there's several, okay? And, you just touched on an important point when you said, oh, I'm sorry. You touched on an important point when you said,
When you said chaos or disorganized, that really describes it. There's several models, and there's many things that go into determining them. The composition of the disk, what it starts out with, what percentage of hydrogen, helium, and other gases, if possible. What types of dust, mostly iron, magnesium, silicon, nickel, carbon, oxygen. Magnetic fields forming plays an important part of this. So actually how the disk collapses, how it evolves, what type of planets settle out of it, it's probably one of the most complicated questions in planetary science right now. And to try to get at answering your question, what is trying to be done in the field right now is to try to take the variation out of this, try to constrain the model by saying, okay, if we can observe a bunch of protoplanetary disks that all have the same composition of iron, but they differ in the amount of hydrogen helium gas, what can we expect? And then you generate a model, you go back, you make more observations, you refine the model. That's what's going on right now. So it is a complicated multifactorial question, no doubt about it.
Great talk for starters. Very, very interesting. So I have two questions for you. I want to talk about selection bias. But firstly, one of the numbers that really flew out at me is when you were describing the tests. You said the cameras operated in negative 770 C. That's like 200 absolute. It's incredibly warm. I was sort of amazed by that number. Do you have anything to say?
yeah, I think what was the goal, I can't speak to
The vast knowledge that the engineers had, but I think they were trying to get a set of conditions that would approximate what you get on the ground when you use a cryo tiger closed cycle refrigeration cooled camera, which is in the general regime of minus 50 to 100.
I got you.
And I don't think it was any more complicated than that. They said, we could cool this thing down to what James Webb was.
Yeah.
James Webb is cooled down to 7 degrees Kelvin, but they have to because that's in the infrared. We're working all in the optical. So I just think it was, hey, let's stick to the regime we're going to be working with on the ground and nothing more than that.
So my second question is, it's really simple. Could you just
Talk about selection bias. Obviously, we don't see everything. Most things we don't see. I have to assume 99% of things we don't see because we're not aligned. So talk about that.
You make an excellent point, and this is actually an important part of the field. When we observe a bunch of stars and we get a bunch of exoplanets, yes, there are going to be selection biases. You're more likely to detect larger planets around smaller stars, and you're more likely to detect planets that are closer into their host star.
Can I also?
No, well, I was going to say about the bias. You use statistics to try to sort this out. There's measures of what's called completeness and reliability. Literally, a woman named Jessie Christensen at Caltech constructs a synthetic pipeline of exoplanet radii and models what you're going to miss and what you're going to catch in each case, so you can get a sense of what your error of detection is and what your reliability is.
Great. I just want to get a.
This is a question from YouTube. Kenneth Couplinger. Is it possible that the transit method that has bias towards detection of exoplanets larger than Earth?
It very definitely does. It very definitely has a bias in favor of larger planets that are closer in around smaller stars, no doubt about it. It's believed with the Nancy Grace Roman Space Telescope, which is going to allow for some measures of gravitational lensing, that we may get down to the regime of detecting Earth-sized planets at about the distance that our Earth is from the sun.
Thank
Just to follow up on that, we did have a presentation here within the last couple of years from somebody who was studying the movement of stars to see what effect gravitational pull might have and how that would indicate the existence of exoplanets. Is there any attempt being made to correlate what you're finding with transiting exoplanets as opposed to alternate methods of finding exoplanets? Not with gravitational lensing, because it's a long explanation, but the system is not set up to do that. As I mentioned, what used to be known as the W-FIRST Wide Field Infrared Space Telescope, now properly the Nancy Grace Roman Telescope. We'll get into that. However, we can correlate what we find by a transit with what we find by a technique called radial velocity measurement, in which you look at the Doppler shift. As the planet goes around the star, it's going to be, the wavelength is going to be bluer as it comes toward you, redder as it goes away from you. You can use that and the principle of the conservation of angular momentum to get the mass in play. So these things can be tied together very closely.
There's another one from YouTube, Roy Patton. Is there a group or several groups of stars that they don't bother to observe, or do they look at everything?
The first mission, the first 2 years of the mission, tested two things. They had what they called postage stamp observations of selected catalog stars. I think it was 200,000 of them, in which they specifically on the test pixel raster had 7 by 7 pixel images of pre-selected stars that came out of a very big filter of surveying the 2 micron all-star survey and Sloan Digital Sky survey. And so we want to look at these critters, and there's about 200,000 of them skywide. At the same time, the whole field of view was assessed by something called the Quick Look Pipeline at MIT, in which they just literally picked every star that showed a transient event from that star field and looked for it for the feasibility of detecting an exoplanet. So they sort of did both, but in the beginning, they focused on specific stars from the catalog.
Have any of the exoplanets that have been looked at, have any of them seemed like they're in the Goldilocks zone at all?
A lot of these stars have numbers that resemble a telephone number. I may get it wrong, but Kepler 462b, I think, is a super, it was discovered by the Kepler Space Telescope, was a super Earth, slightly super Earth planet that is in the habitable zone of its host star. One of the first planets in the TESS survey, TESS 700d, is in the habitable zone of its host star, which is the dimmer late K, early M dwarf, I think. And then many of you have heard of the TRAPPIST-1 system of 8 rocky exoplanets. At least 2 of those are believed to be in the habitable zone. But the habitable zone, you've asked a really provocative question. The habitable zone is a whole concept that's undergoing refinement right now, because what does it really mean? Well, it means if there's the possibility for creatures like, including us, who exist on Earth, won't they have to come into being under the same conditions that we did? Well, yeah, and that's why we use the habitable zone for that reason. But habitability could happen on ocean worlds. There could be entire planets, I'm getting massively into the realm of speculation here, entire planets in which cephalopod-like creatures in the ocean are intelligent beings, and their version of outer space is the water's edge. You know, I mean, you can let your Rhine run free on this, but The short answer is, I think, I may get the numbers wrong, between Kepler tests and other surveys, there's on the order of 30, about 3 dozen planets that are known to be in an Earth-like habitable zone. And they are being followed up with some measure of success and some measure of failure, but whether they have the potential.
I think I remember back in the 80s, it was Carl Sagan talking about some sort of sea creatures that could exist on the moons of Jupiter. So that's well outside what you traditionally consider the habitable zone.
Hey, Rick. You talked about binary stars with exoplanets and multiple star systems with exoplanets. Have you seen any indication that there could be binary planetary systems orbiting any stars?
We have not, to my knowledge, well, I know that in tests, there has not been a planetary pair detected yet. I think the closest thing is that there's some evidence, not from tests, but from another survey of a giant planet that has a Neptune-like moon around it. That's not quite the same thing, but not much in the way of evidence of what you're talking about so far. I think it'll probably come though. And there'll probably be even wackier things than that out there.
You were talking about stars with their dust rings and how they form exoplanets, but I did notice that the ages of these dust rings kind of varied, and there are some other stars that I've heard of with much older dust rings, and I just wanted to know, are these dust rings able to constantly form planets over the course of millions of years, or do they just kind of stop after the star has cooled a bit or is fully formed?
It's a gradual thing, but planet formation mostly, not exclusively, stops when the disk is pretty much dissipated. However, you're touching on an important point, because the amount of time it takes to go from the initial formation and collapse of a giant molecular cloud into a protoplanetary disk depends upon the mass that you start with. On stars that end up being very small, that collapse can take an order of magnitude of 20 to 30 times longer than it does for something that collapses into a giant star. So the time it takes to collapse is also an important factor. But again, to try to answer it, what the point I think you're making is that planet formation pretty much, but not exclusively, ceases when most of the gas and dust has been carved out.
Again, from YouTube, how far away is too far to get reliable data? And
The Kepler mission, which preceded TESS, looked at a narrow area of the sky and went out to about 2,000 light years before it really started dwindling off the number of planets that could be detected. So that's not a perfect measure of how far is too far, but that is a pretty reliable limit. We're not going to see much with our current technology beyond that. TESS is looking out to around 300 light years. TESS is very broad and very close in. In terms of its survey. Kepler was very narrow and very deep. So it's narrow and deep for Kepler versus broad and shallow for TESS. Cool. I'd say 2,000 light years if I had to give a single answer. Thank you.
This is great.
Other questions? I had one question. I might be remembering wrong, but in your last talk, were you primarily using your own telescope for these observations? And now you've moved up to the big leagues?
I'll always be a AAA guy. We started out, a lifelong friend of mine in my hometown of Albany, New York, a guy that I worked together when he was a graduate student and I was an undergrad at an observatory in Albany, New York. He has a backyard observatory, and we've been doing some follow-up of the KELP mission and the Kepler mission. For a variety of reasons, we're still great friends, but for a variety of reasons, not the least of which is something that you will all understand.
The northeastern United States has horrible scene conditions in general. And if you need 9 hours of pristine sky, you need to go to a place like Chile or Maui. Other good reasons to go to Maui too, but you're not going to get a 9 hour, with an absolute pristine point spread function anywhere around here. Not very often. Okay, so we got frustrated in our ability to do it, and my friend Harvey did a few observations in this network, decided it wasn't for him, but I've kind of stayed with it because I find it very exciting. All right, thanks. Any other questions? All right, if there's no others, let's thank Rick for a great talk.
Thanks. Thanks very much. I always enjoy the presentations that don't involve physics, and that didn't. So I can actually stay awake for it and maybe even understand most of it. So thank you very much. Our next meeting is December 9th. December 7th is the astrophotography presentation with our friend from Cyprus, and also the simultaneous conjunction with Mars and the Moon. We have Star Party Sunday, weather permitting, and we're back here the 9th. So thanks very much.
And the meeting, board meeting.
The business meeting is Sunday, December 11th at 2 o'clock. I don't like to conflict with the Eagles, but hopefully by then they will already have locked up a playoff. Oh, I'll put that on there. I'll put that on there. It's Bala Cynwyd. It's not far from the Belmont exit of the expressway in Bala Cynwyd. Okay? I'm not going to put that out over.
I know, yeah, I know.
So thank you very much for coming, and we'll see you next meeting.
So did you guys get a chance to see?
Good night,
Did you guys get a chance to see Hans?
See you next month. Good night, Internet.